Good morning, everyone. It's nice to be here, and I've really enjoyed the talks that we've heard so far. I want to talk to you about sex differences that are passed on from one generation to the next, and help you understand a little bit about a new area of science called the fetal origins of health and disease that has arisen in the last 20 to 25 years and has not yet shown up in the curriculum of most medical schools. It does show up in ours because I'm on the committee, but I'm not sure how that works at yours, so if you're interested in having material about this, you can let me know. So I have several topics I want to cover, and I'll whiz through these pretty fast. I want to talk to you about chronic disease and how it's on the rise in the United States and across the world. I want to talk about early life determinants of disease. Then the maternal stressors that affect girls and boys differently, how male and female parents influence offspring differently, how boys and girls grow differently in the womb, and how nutrition and, I should add, stress are important in these and what maybe all of us can do something about. So the take-home message on the decline of, on the health part of it is that the health of Americans has been declining since the 90s. Actually, it started long before that, but it came steeper at that point in time. And I'll just give you a couple of examples. Here you'll see the number of people that are diagnosed with diabetes starting in 1980. And you can see that that was creeping up, and as a matter of fact, this starts way back in, the data go way back to about 1958. And there are probably not very many people in the room that remember 1958, but I just want you to know that I do. And there were very few cases of diabetes back then. There was something about 1% of the population. And now that's increased to 12 or 13%. And as you'll see, that this increase was slow for a while, and then in the mid-90s it started going up rapidly. And the CDC is hoping that that there's a plateau now that we're seeing starting in about 2014. I hope that's right. But what we do know is that this steep increase was associated with a lot of other kinds of effects too. And we're very concerned about this because I'm a cardiovascular biologist, because it appears that diabetes is a strong predictor of cardiovascular disease. Now I'm going to show you some Oregon data. I always tell people, if they don't know where Oregon is, that it's the state above Hollywood. And when, in other countries, people go, oh yeah, well I know where that is. So it turns out that Oregon only has 4 million residents, and about half of those live in the city of Portland. So what I've shown here is that starting in 1990, this steep part of the curve that I was showing you, obesity has increased from 12% to 30%. And during that same period of time, diabetes went from 4% to about 12%. Now, people with obesity have higher risk for virtually all chronic diseases, as you probably know. But the interesting part is that people who are diabetic have particular increases for risk in cardiovascular disease. And that predicts, as time will go on, that that this increasing numbers will lead to an increase in the number of people who have coronary heart disease and other forms of heart disease. And right now, the Oregon Health Authority predicts that in 2010, there were 225,000 people in Oregon who had heart disease, and they're predicting that to quadruple so that there will be over 1 million people by 2030. And what that means is that virtually 1 out of every 4 people in the state will have heart disease by that time. And the American Heart Association has statistics that show similar rises, not quite that high, but they predict that in the next 12 to 15 years, the amount of money that we are spending on caring for people with heart disease, which is presently about $1 to $1.2 billion a day in the United States, will double. And most of the healthcare models that are being built on trying to help people understand how they can pay for their health care have not taken into account the increases that are predicted, and certainly we have not been doing that in Oregon, where the predictions are even higher than they are for other states. And this can be seen, this increase in health across the centuries are pretty interesting. In this paper in the New England Journal, they showed that if you were born in about 1900, you could expect to live to be about at the age of 50. And by the end of the century, 110 years later, you could see that the expectation was that you would live about 80 years. And also, you should know that 80 years is about 30,000 days. Now, the good thing about knowing that is you can go back and calculate what day you're on, in case you're interested. And the other piece that's interesting about this is that we were predicting some years ago, and the people in this article did as well, that life expectancy would be decreasing from what it is now, just because of the data that I showed you in the previous two slides. So in that case, we're predicting that this 80-year would be going down, and sure enough, in 2016 in December, you may have read it, it was in the New York Times, for the first time in decades and decades, they're now predicting that life expectancy will decrease. And that is that our children and the next generations coming will live shorter lives than we have at present. So that gives us food for thought, and there's a lot of debate about why the increase in diabetes in particular and why life expectancy should be going down. The authors of the article who showed it going down have argued that that's primarily due to increases in predicted heart disease. So now I want to tell you about the early life determinants of disease. Many people have argued about why diabetes rates are going up and obesity, and probably all of those people in the arguments that I've heard are probably have some element of truth to those. We are more sedentary than we used to be. We don't exercise as much. We spend more time watching television. We eat more poorly, and there are many reasons why it might be true. But what people haven't taken into account of very much is that our propensity for having disease is largely determined by our early life exposures to stresses. So I want to talk to you about that. It all started with David Barker. There's a picture of him. And in 1989, he published that your risk of dying of heart disease depends on how much you were weighed when you were born, and that at the 5-pound end of the birth weight scale, you have a much higher risk of dying of heart disease than you do at the high birth weight range. And the interesting part of it is you can see both men and women, and the trends are the same for both men and women. Now, this discovery brought us to make several flaws in our thinking, because we thought that disease and the way we grew before we were born must be the same in men and women. People were thinking that back then, but now we know better. The other thing I want to point out is that there's a slight uptick in birth weights above 9.5, and I'll mention that in a minute. And I'll also mention now that this early study that was done rather crudely in England now has been repeated at least 4 or 5 other times, and allows us to see the very same thing in other countries, including low and middle income countries. So now we think the curve looks like this. My colleague David Barker, who showed these, he and I worked together for a number of years. He died in 2013, and he's the one who established this part of the curve. But he didn't know so much about this part of the curve, which we've learned in the last few years, and that is that the risk for people who are born at the high end of the birth weight scale approximates the same risk, a 3 to 5 times higher risk than babies born at the 8 to 9 pound range, either from low birth weight babies or high birth weight babies. And we now know that particularly this part of the curve predicts a lot of chronic diseases, including type 2 diabetes, obesity, high blood pressure, chronic obstructive pulmonary disease, breast cancer, and cognitive function. All of these are related to the way we grew before we were born, and that came out of the discoveries that were first made by David Barker and now have been studied, and there are thousands of papers on the topic. David Barker also showed that if you include insulin resistance in addition to outright diagnosis of diabetes, that the risk of having those is extremely high, and he showed among men in England that this risk is about 8 times higher for babies born at the low end of the birth weight scale than born to higher. So this 8-fold risk means that the way we grow our metabolic systems and the regulation of insulin and muscle are very much related to how we build our bodies before we were born, and that this is something that we need to take into account. So here's a slide that shows both men and women. This is from the Helsinki birth cohort. The Helsinki birth cohort shows that there's a birth weight effect in predicting obesity in this group of men, and the same similar curve occurs for women. And what we see is that the risk is highest at the low birth weight that we've seen among these Finnish people, and that this increases with birth weight. A group in America from a Harvard group, from Matt Gilman's group, has shown they don't show this increase as much in the low birth weights, but they show this linear increase across the entire birth weight. So there may be some differences in populations. The other thing we've noticed is that the BMI of the offspring at 7 years old and maternal BMI are equal factors to birth weight in predicting the likelihood of having obesity later in life. And I'll show you one more aspect which has to do with high blood pressure. Now this is a complicated slide, so I hope you'll stick with me as I explain it. Along the front here shows you adult weight of males and females in kilograms. So you can see that there are bars here that represent the prevalence of hypertension in these various groups. And you can see that men and women who have low adult weight have the lowest rates of hypertension. Along this axis is birth weight. So the highest birth weights are in the front, and the lowest birth weights are at the back. And you can see that birth weight goes up. That prevalence of hypertension goes up as birth weight goes down, as I predicted for heart disease and diabetes and for obesity. And you can see in this three-dimensional curve that the best place to be is to have a high birth weight with low weight gain as an adult, and the place where you have the highest risk is to have a low birth weight where you gain the most weight as an adult. And what this shows you is what we now call the two-hit theory. The single hit is the birth weight effect, which tells you something about the way you grew before you were born and what your risk factors are. The second hit is what is it that happens to you during adult life that might modify that risk and actually exacerbate that risk to make you more likely to have disease. So why does this happen? Well, we've discovered that there are two main factors that drive your risk for having disease based on the way you grew before you're born. One is structural. And what this little chart shows you that in the brain, the heart, the kidney, and the liver, and some other organs, the number of working cells you have in the heart, or in the case of the brain, the actual wiring of the neurological system, is dependent on the amount of nutrition that was available at the time that those organs were built. So for example, the heart has fewer cardiomyocytes if you were born small, even if you're going to be a large person, because the number of cardiomyocytes that you end up having for your life is set early in your life around the time of birth. The same is true for the number of nephrons in your kidney. Those are all set before you're born, and they are determined by how much nutrient flow you got from the mother to the baby during the time that the kidney was being formed, especially in the last third of gestation. So it turns out that there's a structural aspect, and poorly made organs are more vulnerable to second hits kinds of things that happen in your life that are likely to cause you to have disease. The second one is the epigenetic effect. This is a really hot area of research. It's a lot of the work that I do now in studying how genes are modified by epigenetic modifiers that make you more vulnerable to have disease based on the kinds of stresses you have later in your life. And it turns out that both males and females have various ways in which these two factors affect them differently. So now a lot of people ask how much of what we've seen in this big increase in disease prevalence of chronic diseases is due to genetics. And what you have to ask the question is, how would you judge that? So now I'm going to show you these maps. Here are heart deaths per 100,000 people, and what it shows you is the darker the red, the more heart deaths there are per 100,000. Here are stroke deaths. You can see that dark purple is stroke deaths. Here's the percentage of adults with with diabetes. Here's the percentage of adults with obesity. Here's the percentage of people with hypertension. And here are the percentage of people with depression. Now you can see that there's a geographic distribution of these chronic diseases. And if you want to make the genetic argument, you have to argue that all the people in the South have the bad genes, except for stroke, which is high in Oregon, by the way. So it turns out that not only do you have to argue that they're regionally determined, but not only do they have the bad genes, they have to have bad genes for every single disease. So it turns out that we have to argue that there's an environmental cause, and we're working with a number of economists and other scientists to try to show that the suggestion is that most of this is left from the Civil War and has to do with intergenerational passage of epigenetic effects and current diets and lifestyles. I'll talk more about that if you'd like. Now I want to talk to you about maternal stressors affect girls and boys differently. And I'm talking about pregnancy right now. And I'm going to give you some examples. Here are some examples of people who were born with low birth weight, boys and girls, and that were studied at the age of 9 and 13. And what you can see here is that low birth weight and high birth weight boys and girls have the same percentage of people who get depressed in adolescence, except for girls. And you can see that girls are more likely to suffer depression after the age of 12 if they were born small. Now, the interesting part of this study is that this took a second hit. All of these dots were on the same plane unless there was some stressful event that happened in their life, like a parental divorce or an auto accident or things like that. And then girls were the ones who were more likely to become depressed. Now, there's been a lot of preclinical studies in rats and mice that shows that blood pressure is an example of how nutrition in the womb can lead to various kinds of changes that lead to pathology later. So here we're looking at systolic blood pressure, and this comes from Vickers' article, and what he showed was that those who had ad-lib diets and normal diets have systolic pressure under control conditions. If they had a hypercaloric diet for the offspring, you can see that their blood pressure went up. If they had if they were undernourished before birth, that is, the mother was undernourished while they were in the womb, they had higher blood pressure yet. And if they were undernourished and had a hypercaloric diet, their systolic pressure was even higher. So that includes both males and females, and it's very curious to ask the question whether or not this undernourishment affects males and females differently. And what Laurie Woods showed was that this hypertensive effect actually occurs early in life, shows up by 2 months of age, and continues to go up over the next year. And that the ones who are undernourished before birth are the ones who have the hypertension effect. And this plateaus somewhere around 4 months in animals that were not undernourished, but keeps going up in those that were undernourished. And she also showed that it's the males that take the hit in this case. So undernourished males, depending on whether they were undernourished on the first half or the second half or the over gestation, are mainly affected in the second half of gestation to have higher blood pressures, and that it's not, even though there's a trend to be higher in females, it's not statistically different in females compared to males. And Barbara Alexander has now shown that this requires the presence of gonads in order to do this. And what she showed in the males is if the males were castrated, they no longer were on this trajectory of having high blood pressure, but the castrated males had the same as controls or females of having low blood pressure in the rat model. And she also showed that if you ovariectomize females, and after they're born, that they will show the hypertensive effect as males do. So that there's a very strong hormonal postnatal effect that determines the risk for having high blood pressure later. So I just gave you these examples to show that mothers' undernourishment or maternal stress, which I didn't show you, shows the same thing, can be passed on to the offspring and their risk, especially for heart disease and high blood pressure. So now I want to say that males and female parents influence offspring differently. And I'm going to show you a lot about this because mostly it's women who get pregnant. And you may have read about one case in Oregon where it was the man who got pregnant, but generally it's women. And it turns out that because of that, women have a profound influence on the way that babies grow in the womb. But it's not limited to women. So after studying for many years the birth weight effect, we discovered that there's an effect that goes beyond birth weight and that they're just as powerful as birth weight. One is maternal phenotype. Mother's height, weight, muscle mass, fat mass, skeletal dimensions, hormonal profiles, and blood lipids are all effectors that affect the risk of having disease of the second generation. Fetal sex matters. And also the placental phenotype, its weight, width, and length, and thickness, for example. And it turns out that if you know the maternal phenotype and the placental phenotype, you even know more about the risk for a baby having disease than if you had their birth weight alone. And I'll give you some examples of how we know this. Here's maternal BMI. And maternal BMI is associated with heart disease mortality in adult offspring. We got this we have 3 generations of data from the Helsinki cohort. And what we showed there was the maternal BMI is a powerful predictor of the standard mortality ratio for offspring for dying of heart disease, both males and females. And you can see that women who had high BMI, their offspring have higher risks for dying of heart disease than those that were lighter weight. There's another feature of this has been shown by Tom Fleming. He's written a number of review articles on this if you're interested. And what he's shown is that this effect, the maternal effect, actually begins in the womb, before implantation, and then in the womb. So as you remember your reproductive physiology, that the ovary ovulates once a month on one side or the other, and after ovulation, if there's sperm in the oviduct, the egg is fertilized, and then the embryo goes through a maturation phase all the way down to 8 to 9 days later before it implants in the wall of the uterus. And during that journey through the oviduct, we now know that the developing embryo is getting nutritional signals from the mother all the way along. And these signals are suggesting to the embryo the way it should grow in order to be protective. And I can give you an example, just a teleologic example of how to remember this. So if the embryo senses that amino acids or glucose are low, those are the two best studied, are in low concentrations in the fluid, they will then allocate more cell to the trophectoderm, the cells around the outside, these cells around the outside, and those cells will become the placenta. It's as though the embryo is saying, I can see that the nutrients are low, I need to have a bigger placenta in order to gain nutrients as I'm growing up, and you can remember that as a way to remember this. But I just want to tell you that the embryo can't really think, so it's not doing that through mental process. That was a joke. Okay, now I want to tell you about why this is transgenerational. Here is a mother. She's a grandmother. She's talking on the phone with a cord, so it's a long time ago. And she is pregnant. And in her womb is a baby girl whose reproductive tract is growing, And this baby girl is being nourished by this woman's diet and her body, the turnover of fat and protein. This turnover is changing the reproductive tract and is nourishing the egg in the ovary. So later, this baby girl will become an adult girl. She'll talk on a phone without a cord. And it turns out that she'll eventually become pregnant. And when she does, the baby that she bears will come from the egg that was made in her ovary that was nourished by her grandmother. So what that means is that the ova in the ovary are actually being nourished at part of the time in their life by the grandmother and not the mother. And during that time, this gives what we now call epigenetic opportunity. That is, that's the opportunity for the epigenetic profile of the genes in those eggs to be modified by the nutrition of the grandmother that will eventually make a difference. So we believe now that the risk for this baby having a disease later in its life is not only determined on its mother's diet and body, but also in the nourishment it got from its grandmother. So the other interesting part of it is that the entire reproductive tract is grown. The number of glands and the thickness of the endometrium and other features are determined during this period of time, and those are determined by the grandmother's diet. So I'm going to show you a picture I really like, which comes from the NIH archives. And here's a picture of 4 generations of women from a photo from 1931. In 1931, this baby was 2 years old, and she's now in her 80s. And you can see that this 2-year-old was born to this mother, but she came from an egg that came from this woman's ovary that was nourished by this mother when she was in her womb. And you can see that this 88-year-old woman can now have some effects that came from a woman who was born in 1879, right after the Civil War. So you can see that this is what we call the 100-year effect. In this case, it's a little more than 100 years. I can use myself as an example. My mother's in her 90s now. I just went to see her last week. She's doing well. And the egg that made me and my propensities for having chronic disease as an older adult now were determined by my mother in her womb about 100 years ago. So it turns out that this 100-year gap in generations is really important for us to understand, because the health of individuals is not just what happens to you on whether you ate cholesterol for breakfast or not. It has to do with the stress and diet that went back for 2 generations in your life. And another example is this woman was born to this woman, and the egg that made her was nourished by this woman, and that doesn't look like a good proposition to me, because she was born before the Civil War and goes back a long period of time. So now we can start thinking about nutrition and health of our population based on transgenerational effects, and we can now start to understand why disease rates are now going up so high across the entire population, and I'll bring that up later. So lastly, I want to point out to one more paper, and this is a paper by Kelly Moley at Washington University. And what she did was she took mice and gave the mother mice before they were pregnant a high-caloric diet, the so-called cafeteria diet. And after they got pregnant, she studied their offspring for 3 generations. And the part you have to know is that after that, the F1 generation was not put on a high-fat diet, it was put on a normal mouse chow. And for the next 3 generations, she studied their mitochondria and found that there were effects that were seeing defects in mitochondrial function for the next 3 generations. And these occurred through the oocytes. And it turns out that the genes that were affected in the mitochondria were these genes, DRP1, OPA1, and the mitofusin genes. And it turns that these genes and the expression of them were passed on through the ova from one generation to the next. So this shows a very strong maternal effect, transgenerational effect. We also believe that there's a male effect. Now, how could this occur? All of these things are likely to be mostly epigenetic that go across generations, as you would guess. And I don't have time to explain epigenetics because most of you will know about it, but there's some features of it that are particularly interesting, and here's one. And one is that identical twins like these can have different fingerprints. Now, we always think that genetically, morphologically, that identical twins are the same because they look alike, but it turns out that they can have different fingerprints. And the reason they can have different fingerprints is because your fingerprints are determined by your nutritional levels at about 13 to 15 weeks of gestation. In fact, there's a colleague of mine at the CDC who claims that he can predict people's likelihood of having diabetes based on their fingerprints as well as their birth weight. And so why do these two have different fingerprints? Because they got different nutrition. Yes, they're identical twins, but they share a placenta, and inevitably one is more likely to get more of that placenta than the other and to get different nutrition, and they often die of different diseases too because they have different epigenetic propensities. And these epigenetic changes can be methylation of promoter regions or other parts of DNA and the CPG islands. This can be histone modifications that occur, and particularly methylation of histones that change the likelihood that genes will be available for transcription, and non-coding RNAs that modify the way that the gene products are actually processed. These epigenetic effects, we now know, can be, in certain cases, passed on from one generation to the next. And here's an example of an epigenetic effect due to methylation. So here's methylation is increased with low maternal carbohydrate increase. That's the first thing you have to know. And what you can see is that when this group in Southampton, England, looked at children of 9 years old and compared that to the methylation of white blood cells that they were carrying, you could see that the RXR gene, the retinoic acid receptor gene, was more highly methylated, and that the child's fat mass was actually related to the methylation of that receptor. And it turns out that they were worried about whether this is true or not. They went to a different village and did the same measurements, and they found the same thing. So it turns out that the methylation of genes that occurs because of nutrition, and in this case low-carb diets in mothers, was the problem. And you can see that if you look at carbohydrate intake across various groups, that the low-carb mothers were the ones who had the highest methylation percentage of the RXR gene. And this gives a caution which we already knew from other studies, and that is that women who eat high-fat, high-protein diets with very low carbs, you can probably know some of what these diets are, can have babies that are more likely to be obese later in life and be hypertensive because a balanced diet is required for the proper methylation of genes. So there are some other examples of this. Here's the risk for hypertension according to the placenta. I'm just going to give you an example now of how the placenta modify it. And you can see that for women, the odds ratio of being hypertensive was dependent on the area of the placenta, but not for men. These are women offspring. But for women, mother's height had a very profound effect. And it turns out that women were more likely to be hypertensive if their mothers were short and their placenta was small. And as I said before, there's a powerful interaction between placental size and maternal stature and BMI that determine risk for disease in the offspring. But what about men? So here's a man, and it turns out that we know very little about men, and unlike almost all studies in the world, and all the ones that have been mentioned this morning, women are mostly overrepresented in studies of offspring. And there are very few studies from men. There are a few, and all of them show that men who have poor nourishment before fertilization are likely to have offspring that are more likely to have disease. So here's one that defines offspring chromatin and intergenerational obesity. And here's another one that says that there's more likely for diabetes to occur if nutrition was poor in the father. So we need a lot more research in this, but I just want to make sure you know that there is a paternal effect because men have been feeling left out. So lastly, as boys and girls grow differently in the womb, I want to say a little bit about that. Here's studies by Michelle Lample, and what she showed from pregnancies in Chile is that at any given maternal height, boys have higher birth weight compared to girls. And the same is true for maternal weight until you get to really higher weights where the difference is less. And it turns out that maternal height is more of a predictor for birth weight differences between boys and girls. So that leads us to understand a little bit about how the maternal body can affect how a baby is born. And now I'm going to give it to you in big categories and a generalization that you can remember. So people who suffer from a lot of body weight generally have what most Americans have, and that's what we call high-calorie malnutrition. And that applies to almost everybody sitting in this room. Because it's very easy, because of industry's way of giving us food, to eat a lot of calories, but it's very difficult for us to get our nutrients. So we all suffer from high-calorie malnutrition because we eat calories, high calories, low nutrients. Women who suffer that in a great deal, and especially have a lot of body fat when they get pregnant, are likely to have babies that are either macrosomic, have a lot of body fat, or who are very small. So the normal distribution is spread out among women like this so that their babies are more likely to be born in one of these two categories. Women who are malnourished because they are very thin, and especially who want to be models like this woman, who basically have eating disorders because they don't eat very many calories and they eat very few nutrients. And in that case, they have very low muscle mass and no fat mass. And in that case, the turnover of body and muscle cannot provide for the babies, and they're more likely to have babies that are in this small weight category. But it doesn't matter. Babies in either category, at the extremes, as I showed you earlier, are more likely to have livers that will produce poor blood lipid profile and dyslipidemias, increased appetites because of the way their brain is wired, and higher oxidative stress that leads to endothelial dysfunction and a higher likelihood that they'll have plaque in their arteries, especially in the brain and in the coronary arteries. So the risk factors that come from these two extreme babies include the dyslipidemias, high blood pressure, procoagulation, and a sedentary lifestyle later, which, by the way, we don't understand. So there's a difference between girl babies and boy babies. This is a very interesting fact. And what it says is that boys signal their mothers differently than girls do. And we've discovered that the birth weight of boys can be up to 200 grams higher than for girls. On the average, it's about 100. Boys grow faster, and they invest in their placenta less. So we wrote a paper called Boys Live Dangerously in the Womb. And the reason they do is that they want to get as much nutrient from their mothers they can get without having to build the placenta. Now, why don't they want to build the placenta? Because it takes a lot of tissue acquired to build a big placenta when that tissue could be used by the baby, right? So there's an optimal ratio between placental weight and baby weight. Now, boys cheat their placenta, have a smaller placenta, and therefore, under condition of stress, they're more likely to die in the womb. Maternal energy intake is increased by 10% in women who carry a boys. They eat more protein, they eat more carbohydrates, and they eat more lipid. And this diet, this increase is driven by appetite changes in the brain that are signaled by the baby. We don't know what those signals are, and if you want to do a research on that, it would be wonderful to do it. So I'm now going to move and talk to you about why we need to change our food culture and how this all relates to adult disease. First of all, before I talk about food, though, I'm going to mention the issues of toxic stress. This lower curve shows the cortisol levels in normal people, and you can see that they're low during the night, they go up early in the morning, and that every time you eat, they go up a little bit, then they go back down at night. However, people who suffer what they call toxic stress or unremitting stress or some kind of social stress, women who suffer while they're pregnant because they're abused by their spouses, they don't know how they're going to pay their rent, or they live in adverse conditions. Those women have higher cortisol all the time. And they have higher peaks during the day, and if they have a stressful event, it goes even much higher than that. And cortisol crosses the placenta, especially at these high concentrations, and leads to a number of issues with the offspring, including reduced uteroplacental blood flow, reduced fetal growth, preterm delivery, spontaneous abortion, more malformations, and chronic disease risk. And this risk is passed through epigenetic means to the F2 generation. So it turns out that this stress is equal to nutritional stress, and in most cases goes along with nutritional stress. So I'm going to make this point about how this turns out to affect the way babies grow. So intergenerational malnutrition I've talked to you about, poor maternal diet, maternal phenotype, chronic social stress, and paternal contributions all impact on the way the baby grows, and when these are detrimental effects, they lead to a baby that has a pro-inflammatory state, and second hits like stress and poor nutrition later in life will bring the manifestation of chronic diseases like diabetes, hypertension, heart disease, and obesity. So how does this work? It's intergenerational because if you have a healthy mom who has a healthy diet and has a healthy baby, that baby will have normal childhood growth. It will be resistant to disease as an adult and will not be expensive even into the aging. However, if an offspring, even if born under these conditions, then starts eating a poor diet before and during pregnancy, this is supposed to be junk food, it turns out that this offspring will be programmed, it will grow more poorly, and it will have rapid childhood growth if it's born small. That's called catch-up growth, and it will have more expenses than in the normal child. So it'll cost us more in terms of disease. This baby will go on, if this baby turns out to be an obese mother or father, and they're on a really poor diet, they have a double hit, they have poor nutrition, vulnerability for disease even early in childhood, second hits in later life cause toxic stress at home, or poor diets, as we see in much of our population in Oregon. And these people lead to a lot of chronic disease, and this is what our society has to pay for in terms of healthcare costs. And we now know why this has gone up, because we are now in the third generation of eating processed foods in this country, and we have low nutrition diets for just about everybody. And to make this point, I can tell you, I'm not going to show you the slide, but the American Heart Association looks at the percentage of all the risk factors that are found across in society, including diet, smoking, exercise, and all those. And what they've found is the worst risk factor that's being cared for is diet, and they predict that only 0.5% of Americans eat a healthy diet. And that means that most of us don't, and because of that, we pass on the outcome of those poor diets to the next generation. So we can't blame mothers for this any more than we can blame fathers. Mothers are not at fault because the mother's environment is presently nutritional stress, social stresses. We're dealing in Portland, I don't know about in your city, but we're dealing with a lack of housing. And it's the poor people and the young poor people, many of whom are pregnant, who are being kicked out of their homes so that people can get better rent rates now. So this is a huge problem. And housing and social stress go right along with all the other issues we have to face in understanding the physiological underpinnings of disease for people in our culture. We have social stress and chemical toxins which are in all of the environments in which we live, and which, according to my calculations, based on present policies, are likely to get worse. So remember that the mother is the environment of the baby for sure, but our society is in the environment of the mother, and that's what makes the difference on whether disease occurs or not. So let me tell you what I've told you. I've told you that chronic diseases are on the rise in the U.S., and I'll just say right now that from our studies both here and in the South, we believe that's because of poor nutrition that has increased over the last 3 generations. And in many cases, increases in stress in lower SES population. Much of the disease risk we have is determined early in our lives. And I don't know if you'll remember the hypertension slide, but people who are born small and put on weights of adult people in that category, 70% of them will have high blood pressure. So it's a huge effect in the population. Maternal stressors affect girls and boys differently. And it turns out that maternal stressors, either stress or diet, can affect boys in the way they grow and girls in the way they grow. Male and female parents influence their offspring differently, and females carry the babies and have a larger influence on the way those babies grow. And boys and girls grow differently in the womb. Boys are greedy and girls are not. And last, I want to make the point we have to change our food culture if you want to do anything about this. And I'll point out again the TED Talk that was referred to. Everything I said you can hear in 10 minutes. Thank you very much.